Today, we'll start off with some of the typical challenges that our customers are facing within the context of seismic processing and interpretation. Over the years, by working very closely with our customers, some of the key challenges that they face on a day-to-day basis, particularly in the context of seismic processing and interpretation are, firstly, because of your fixed compute capacity on premises, the seismic processing itself takes too long. Secondly, the data is oftentimes siloed across organizations and teams, and it is oftentimes not easy to access. And finally, after the processing is done, when it comes to the interpretation, again, the seismic interpretation is, again, very much manual today and also siloed across teams. Next slide, please. To address these challenges at AWS, we actually work backwards with our customers by continuously hearing to their requests and feedback. And we have developed a number of key HPC services, particularly suited for addressing the customers' challenges for seismic processing and interpretation. Everything starts with the data. That's why you see here storage and data is in the central piece. In the context of seismic processing and interpretation, we have a number of high-performance storage-related services, such as S3 as well as FSX for Luster. And of course, once you have the data, the next step is to go ahead and process this data. So we provide on-demand compute resources for our customers so that they can tap into the scale that they need in order to be able to complete their seismic processing. And lastly, when it comes to the interpretation and the modeling aspect, we also offer a variety of accelerated GPU instances, particularly suited for AI and ML workloads, as well as remote desktop and visualization aspects. Next slide, please. At a very high level, this is the entire stack when it comes to running HPC workloads on AWS, such as seismic processing and interpretation. As you can see here, everything starts with the data, whether it is a terabyte or hundreds of terabytes or petabyte scale data. We have services like Data Sync, Snowball, Snowmobile, or Direct Connect, which enables our customers to move data from your on-premises into the AWS cloud at a much faster speed. Similarly, in the context of compute and networking, we offer more than 270 compute instance types for a variety of workloads. You know, in the processing world, you have workloads like Kirchhoff, RTM, FWI, etc. And each of these workloads have the underlying physics slightly different, which demands a different type of compute as the workload changes. So to address that, we have a variety of compute instances for our customers. Similarly, we talked about storage. Again, a number of high-performance storage options, including S3, which is our object storage, as well as FSX for Luster, which is a high-performance file system. Similarly, when it comes to orchestration, we have a number of services such as AWS Batch, which helps our customers streamline their workloads so that they can run workloads at scale. And finally, when it comes to visualization, or what we call as post-processing, we offer services such as a DCV, which is desktop cloud visualization, as well as AppStream, which is a fully managed service, so that customers can run their geoscience applications within a browser, and all the heavy lifting is done behind the screens by AWS. And to summarize, these are the key reasons why our customers cite when they pick AWS for running their data-intensive and compute-intensive exploration and production workloads, such as seismic processing and interpretation. Firstly, AWS has the highest operational reliability. Secondly, we have the broadest and the deepest cloud platform. We have more services and capabilities within each service than any other provider. And in fact, our innovation in the context of high-performance computing has been recognized at the recent supercomputing conference last fall, where AWS received 6 different awards for a variety of categories. AWS also has the most energy domain expertise to address the needs of our customers. And finally, when it comes to the culture of innovation, as mentioned earlier, we always work backwards from our customers to address and solve their biggest business problems. With that, I'd like to pass it on to Matt for the rest of the presentation. Thank you.
Well, I'll take it from here. I'll be your co-host for this webinar for the remainder of our time together. And again, my name is Matt Morris. I'm the Director of Product Management here at Bluware. And Srini just gave us a real brief introduction on how AWS can fit as a cloud solution for oil and gas. And I'm going to show you a practical application of what you can do with all of these resources. And I'll do that with an application called InteractivAI. You probably know what the AI stands for. Today's webinar is really going to stay focused on the interactive nature, because I think that's really the cool and interesting part about this piece of software. So we've worked together for about an hour. It's my hope that when we're done here, that you come away with some new insights on the following 5 topics. First off, I want to do some level setting and offer maybe a philosophical perspective on when it makes sense to use machine learning in geoscience workflows. Next, I want to say a little bit about volume data store, or VDS. That is really the underlying enabling technology that makes our ML engine so performant that it's interactive. Third, I want to address the geoscientists in the audience and talk about what it means to move your geophysical workloads into a cloud environment. Maybe help you put together a mental model on how all of your IT infrastructure is organized behind your application. Fourth, I'll do some introductory remarks on what interactive AI is. It's a very different way about thinking how to interpret seismic data, so I want to set the stage and talk about the philosophy of use. And then lastly, we'll get to the fun part. I'll run through a demo of interactive AI. Should take about 15 minutes, and we'll do a workflow from absolute beginning to end. So with that, let's jump into some use cases. And I want to begin with a big bucket of cold water. When does it make sense to bring ML into a workflow? I'll tell you, ML is a very shiny new tool, and I can't browse LinkedIn nowadays without some data scientist showing me a cool ML project that they're working on. And that's cool, but there's actually a lot of really useful software out in the world that's still useful, even though ML is a very fashionable thing nowadays. So before your data scientist goes off to build an ML model to solve a problem, I would suggest that there's a certain number of prerequisites that ought to be met before you go down that path. And the first and most obvious is, do you already have an analytical solution? So if you have a physical model, it really makes zero sense to try to go down the more implicit route with machine learning. And if you don't have a physical model, could you invent one? Could you come up with an empirical solution or something that's more model-based as a substitute for the analytical solution? And again, if the answer is yes, then you probably shouldn't be delving into the world of ML. Third, you need to at least intuit a relationship between the data you've got and the quantity you're trying to predict. Because ML is clever, but it can't invent relationships in nature that don't exist in the first place. Next, a very simple question. Do you have enough training examples to train the network? Training images is like the gasoline that ML engines run on, and if you don't have any, you're not going to get any useful results. And lastly, to be brutally pragmatic, you ought to be asking yourself if the costs and the resources required to build an ML solution is really going to be a net gain over rather just solving the problem by hand. So if you can get to an affirmative answer on all these questions, then there actually are quite a few problems in geoscience where it does make sense for machine learning to be brought into your workflow. So to put that in more tangible terms, here is a list of features where we don't really have any good deterministic algorithms to detect a feature in seismic data. So if it's your task to sit in front of a seismic data set and try to extract one of these features from the data set, then really, what you're doing is object detection, right? And that's a domain where an awful lot of the innovations in data sciences are happening right now. And so today, we're going to focus on one of these features here in green. We're going to look at faults, mostly because that's the feature that's attracting the most attention nowadays. But we can use interactive AI to detect other features that are on this list. But I've only got an hour here, so we're going to try to stick with just one. Well, the assertion that I'm making today, it's pretty straightforward. If it makes sense to bring ML into your workflow, then using a deep learning approach is going to make you either a faster or a more productive interpreter. If you're not worried about speed, then it's going to deliver a more thorough solution than what you can do with your eyes and hands alone. So I'll try to back up that assertion when we do our demo here, but that really is the thrust of the talk right there. So it's going to be a combination of the subject matter expert and the deep learning engine working together. And that's really the value proposition that interactive AI is putting into the market. And what I'll try to make plain in the demo is that it's not you versus the machine. You're not going to be competing with each other to detect faults. The two of you are going to be cooperating together, and you're going to be slowly making each other better. And that's why we've called the application interactive AI and not like, I don't know, steal your job AI. It's going to be you and the machine working cooperatively. All right, well, let's look at volume data store. VDS is just a way to store and retrieve seismic traces. So most people's minds go to SegWy when they hear that. And, you know, that's fine. It's a very old format, and nowadays, really, we just use SegWy to archive data. Anytime you want to work with seismic traces, the first thing the application is going to do is you're going to recode them into some alternative format. Well, Bluware's been working on VDS for like 15 years. It's a long time. And in the past few years, we've recently re-architected the format in order to be cloud native. And what that means is the traces are arranged as an object rather than a file in a file system. And there's some good technical and commercial reasons to do that, not the least of which is it assures really fast access to the traces and when you're trying to make random pattern calls into the data. And because of that, it is one of the reasons we can run deep learning as quickly as we can. Now, there's a handful of other really interesting features that are part of the VDS standard, and I wanted to touch on them individually. So first is this adaptive streaming capability. This is something that I'm sure we're all quite familiar with, even if we don't realize it, because it's the same thought process that's present with Netflix. So Netflix stores movies up in a server in somebody's cloud somewhere, and their job is to stream RGB pixels to your client device. So those movies are stored with a particular audio-video codec called H.264, and that's a set of standards, and one of the standards in there is a way to compress the video stream. And the algorithm that they've chosen is called a discrete cosine transform. And that happens to be the same algorithm that we've chosen to compress our seismic traces. But instead of compressing pixels, we're compressing the wavelet. And then there's a second really cool trick that Netflix does, and that is it pays attention to how much bandwidth your client device has available. And so Netflix is always trying to optimize the trade-off between buffering and video quality to try to make sure you get a great experience. Now, we don't care so much about bandwidth limitations with VDS, but we do pay attention to the use case of what's consuming the seismic data. And that's called a level of detail streaming. So if the data is going to be consumed by somebody's eyeballs, like a human, you actually don't need a very high level of detail. But if you're going to be doing detailed computations on the data where that fourth or fifth decimal order place matters, then we could change the level of detail and crank it way up. And so there's always going to be this trade-off between performance and precision. And so VDS is going to optimize that data pipeline to depending on whatever your use case is for the seismic data. All right, the next thing I want to touch on is that the format uses compression. So if you have a SegWy that's sitting on your local disk and it happens to occupy about 1 gigabyte of space, then if you process that file over to a VDS format, it's going to be compressed by about 75%. And that's with our standard recommended amount of compression. So it's perfectly reasonable to do most geophysical workflows with this sort of compression in mind. Matter of fact, back in 2017, when I was working for an operator and I was doing my due diligence trying to understand this format, I ran a set of tests against VDS and SegWy to see if I can detect any difference. And the answer was essentially no. It was negligible. It really didn't affect any workloads. However, some people are principally opposed to lossy compression on their seismic data. So we do have a lossless storage option, which will be a bit-for-bit representation of your parent SegWy. The next thing I want to touch on is really important. This is probably the second most important slide I'll share with you. And I'm going to tell you a little bit of a backstory here. I first got my toes wet in deep learning on seismic data back in the summer of 2017. And I had a data scientist and a data engineer and a couple other geologists. And that was our mission, to see what we could do with these new technologies. So we invented this workflow that you see along the top here, where we would start with a SegWide data set, and then the data engineer would extract all the inlines and cross lines and turn them into images. Those things would get chopped up and randomized, and then we would arrange them into a record file. And then the data engineer would pass that off to the data scientist, who would pass it through the neural network. And then we'd take a look at our results, and we'd invariably have to iterate, either change our labels or change some detail in our network architecture, and we would do it again. And once we got good at it, once we were up and running in like a production sense, we were passing like a survey per week through this workflow. And then the Bluware guys came into my office and said, "Hey, Matt, check out this cool tech we're building here." And I looked at it, and I just leaned back in my chair. What was taking us a week, these guys were passing through in a couple of minutes. And I was just really taken aback at what a step change it was, and how many new possibilities that was going to open up for deep learning on Seismic. And in fact, that's a big reason why I came to work for Bluware. So this really is the heart and soul of what makes interactive AI work in a manner where we can think of it as interactive. One last thought I want to leave you with about VDS, and that is we've recently open sourced a flavor of VDS that's called OpenVDS. And so today and forevermore, it will be free and completely free. It is the preferred standard for storing seismic data in OSDU. So if you or maybe a data scientist wants to build some sort of cloud native application and it's going to handle seismic data, then you're likely going to be touching a VDS file and making API calls onto it. You can see a lot of these good features are freely available in the open source spec, but Bluware has retained a handful of these features and built a business case around their implied value proposition. One last thought that I want to leave you with is that if you ever run into a VDS file in the wild, whether it's the open source flavor or the commercial flavor, you can always read that file. You can always convert it back to SegWide. We're not really interested in imposing any sort of lock-in on the customer base. We want this format to be like freely chosen based on its technical merit. All right, let me speak to the geoscientists in the audience and talk about some of these new ways of working. And I want to begin by getting on my soapbox for a minute here. And I'll say to you, you might consider getting an AWS Cloud Certification to stay up to date. And I say that because back in the 90s when I got my very first computer, I think it was fine if you knew what a hard disk and a CPU and system memory was. And you know, if you could get around on like a command prompt, you're probably ahead of the curve compared to everybody else. And then the 2000s came along, and suddenly we had to become familiar with what the web was, and email started permeating everybody's office. And so we had to get comfortable with the idea that the data that we needed wasn't always on the box on top of our desk. And so we had to start appreciating client-server relationships, and you had to have some sense of awareness as to whether or not your data was local on disk or memory, or if it was somewhere else in the ether. And now here we are in the 2020s, and we're watching an awful lot of IT services become completely industrialized. And what I mean by that is it really doesn't make a lot of sense to make your own IT part when there's a factory down the road that's already built it and tested it and can deploy it instantly. And they can probably rent it to you a lot cheaper than you could ever build and maintain it yourself. And that's pretty much the value proposition of all of the cloud business going on right now. So I know most of us don't have any aspiration to become an AWS developer or a cloud architect, but there is this foundational certification that you could sit for. And in my experience, if you train for like 1 to 3 months, you can sit for a 1-hour test and get this certification. And you can either show it to your employer or maybe your future employer. And really what it does is it shows you have some sort of baseline understanding as to how cloud technologies work. And I personally think that's going to make you a better knowledge worker, even if you're not an IT professional. Okay, enough of my soapbox. Let's look at an architectural diagram of interactive AI. Here's you. This is supposed to be you on the bottom left here, and you're sitting in front of a commodity laptop. So that could be a Dell Inspiron or an IBM ThinkPad. It's whatever standard issue you get from the company. Really, the only requirement is that you have an internet connection and a web browser. And because what you're going to be doing is you're going to be making calls on the ActiveAI server, where all of the heavy lifting is going to happen. And for our purposes today, that server is going to exist in AWS as an EC2 instance. Now, EC2 is just the name that Amazon gives their virtual machines. So there's a whole stack of machines out there, and you reach them and interact with them via EC2. And we've selected a G4 instance of EC2 because these machines have been custom made to do machine learning. They're nicely spec'd out, but most importantly, they've got an NVIDIA GPU on there, which is stuffed to the gills with tensor cores. And that's bespoke silicon that's been purpose-built to do deep learning calculations. So it pairs up nicely with the application that we've built here. Well, that takes care of compute, but we also have to store our data somewhere, and we're putting our VDS seismic data sets in AWS S3, simple storage service. Now, I mentioned earlier that the seismic is stored as an object, and that's what S3 is. It's an object storage service as opposed to a file. File systems are slower and more expensive, and it makes a lot of technical sense to store data as an object when you're accessing seismic. And lastly, Srini touched on this, but if you're wondering how to get data into S3, you've got a handful of options. You can either rent an appliance called a Snowball, which is just a secure little computer that you copy your data onto, and then it's shipped off to AWS. Or you can just establish a direct connection between your data center and AWS, and that'll provide a secure and high-speed link if you want to send the data up the wire. But before I leave this slide, I want to make this crystal clear that you can run the application on really anything that has an internet connection, practically speaking. It doesn't matter if you have got a high-powered GPU or how much RAM you've got. All of the computations is going to happen behind the scenes on the server. So that makes starting InteractivAI trivial. All you're going to do is fire up a browser and click a link. And what's going to happen behind the scenes is that you will spool up an EC2 instance. Once that thing becomes available, InteractivAI will start the service up, and then it'll start streaming seismic data directly into your browser. Of course, all that's going to exist inside a virtual private cloud, which is wholly owned by your employer, and nobody else in the AWS environment can access that green box. If you're not an AWS client, we're happy to load InteractivAI on your on-prem data center. Either Windows or Linux flavors is fine. And then lastly, if Hurricane Linda blows your power and internet away, you still don't really have an excuse to stop working because the application is happy to run locally. So this is an instance where the server and the client happen to be the exact same machine. All right. Let me move on to the next section here and say a few words about the application. All right, well, here is InteractivAI in its full glory. This was a screenshot I took last week of my web browser. And anybody who's spent any time interpreting seismic data on a workstation will be instantly familiar with most of this UI here. We're looking at crossline 4750 of the Perry Haka dataset, offshore New Zealand. And along here on the bottom, we've got a film strip, which is a list of all of the cross lines that are available to stream. And then these little green ticks are all of the lines that I have labeled or interpreted in order to train the neural network. Over here on the left, you see some widgets, some tools. You might be inclined to think that those are interpreting tools. You'd be half right. They're actually labeling tools, because there's a bit of a different mindset in place when you're labeling seismic data for a computer rather than interpreting data in order for some sort of business decision to be made. So we've built this application from the ground up to be a labeling workbench. It's not really necessarily trying to compete with Petrel or anything to be an interpretation platform. So all of these tools exist solely to get your seismic data labeled and to get a network trained up. The last thing I want to point out are these three buttons down here at the bottom. The first toggle is the training toggle. It's in the off state right now. But when you turn that on, you will be firing up a whole bunch of Python scripts that start getting busy in the background. And you can leave that on indefinitely. So it's happy to train for a minute or an hour or for days if you like. It just depends on how much precision you want to pursue. But once you're done training, you flip that off, and now you can flip on the inference button. And an inference essentially is just what the machine has learned applied to a line that it has yet to see. And then right next to that is the labeling button where you can turn your own labels on and off in green. So if you're starting to string this together, the person's interpretation is going to show up on the screen as green. The machine's interpretation is going to show up in yellow. And your job or your task with the application is to get the yellow to look as much like the green as possible. And that sort of leads me into this last slide here. And this is, I think, the most important slide I'll share with you today, because this is a very different way of thinking about interpreting seismic data. So let me walk you through this workflow here. On the inner loop, we've got you sitting in front of your computer, and on directly opposite from you is the ML engine. And the first thing that will be happening is you will be asking for seismic lines, and it will stream those to you so you can start thinking about your data in any sort of orientation that you like. Now your job is going to be to start providing expert labels based on that seismic data. Those labels are going to cycle into the machine learning engine, and it's going to start putting together a set of weights, and it will use those weights to develop an inference. And then you will look at that inference and you'll decide what needs to be done next. You might train some more, or you might add some more expert labels. In either case, your job is to be very precise, because you're training a computer and not another person. You're going to need to be very comprehensive. You can't just label half a line, or otherwise you're going to confuse the network. You're going to need to be objective, and by that I mean you can't put labels down where you think a feature exists. You have to be a bit more aligned with what the data actually says. And lastly, you need to be interactive, and that means reacting to what the machine is suggesting to you. Once the inference comes out, your job is to fine-tune the details that the machine missed, maybe fix what's not quite right, and then add things that either you or the machine is still missing. So this becomes a bit of a virtuous circle, and you know you're done when the machine inference more or less matches your expertise when you come back to label the data. Essentially, when there's no daylight between the labels and the inference, you're done. You've got a well-trained network, and then you can apply the network to the remaining, say, 99% of the data set that you did not label. All right, let's see that live. So I'm going to pivot over to the demo. We're going to step out of the slide mode, and we're going to look at the application do its thing. All right, here we go. Looking at my desktop here, we're going to fire up a browser, and I'm going to browse over to a domain that will resolve to an AWS data center. So production.trial.bluware.com. So here we are in AWS running in the browser. This is version 2.1. We could create a session if we like, and maybe give it a sensible name. Oh, how about Bluware AWS demo? I'm actually going to skip over that and dive straight into the preloaded volume here. So right now we're initiating an EC2 instance. The GPUs are booting up. The server will be starting on that VM, and then we're going to stream some data directly into the browser. All right, everybody's up and running. So here we are. Here's some seismic data. This window is 3D accelerated, so you can zoom in and pan with your mouse just like you'd expect. Down here along the bottom, we've got our navigator. We can set our step size to 20, and maybe I'll step down to inline 2030, have a look around. Okay, there's some decent faults here that I could start labeling, but before I do that, I want to do a party trick. I want to put the domain name in my clipboard, and then I'm going to kill the browser, like the power went out or my cat walked over my keyboard. So now I'm going to recover the browser. I'm going to point it back at where I was just at, and I'm going to have to re-enter my credentials to make sure I am who I say I am. Whoops, try that again. And there's my session that I was just in. And then we're right back where we started. So the message here is everything is stored server side. Again, nothing important happens on the client's machine. It's all taken care of on the back end. So there's different color bars here, whatever floats your boat. I'm going to be interpreting a structure, so I think I will stick with the black and white color bar. Now this is a little bit squished for me, so whoops, let me turn on the vertical exaggeration and stretch that out a little bit. Just looks a little better to my eye that way, so we'll leave it right there. Okay, so now I need to poke around and find a place where I want to start labeling. Let me set my step size to 20. If I step to the right, I'm finding that there's quite a few more faults. There's a lot of faults on the right side of this survey, and if I come to the left side of the survey, it's a lot quieter. Now, I'm pretty lazy, so I think I'll get started labeling on the left side of the survey. One last thing, I'd like to find maybe an even number, a nice round even number, because I like to label evens. How about 2060? Good place to start. So I'll pull a widget out to start labeling. I'm going to set my brush thickness to 8 and give her a go. Oh goodness, that's really thick. That's a lot thicker than I'd like to be. So let me press undo and thin my brush down a bit. How about 3? All right, off we go. Gonna start labeling faults. Got my headphones on, having a good time here. Here comes fault number 1. All right, it's my job to label this line in its entirety. Don't worry, we're not gonna sit here and watch me do this in real time. I'm gonna drink some caffeine and we're gonna speed this up to 8x. All right, so off I go. Mark, mark, mark. And then I'm going to step to the next line. You can see down at the bottom, I'm on line number 2 of my labeling effort. Let's get these faults scratched in here. And then I'm going to step to a third line a little bit toward the center here. I find this quite soothing to watch people scratch faults in, like watching Bob Ross paint. Happy little fault here. Another one here. All right, I'm going to kick off training here. So we've labeled 3 lines. You can see there's a marquee bouncing back and forth up along the top of the browser. That means the labels and the associated data is being streamed into the engine. It's being randomized, making sure that classes are balanced. And then now that the progress bar is marching, that means training is underway. So the progress bar is indicating an epoch. This is the very first epoch of training. I'm going to keep this real time because I want to make it very clear that this is happening in real time and it's going to take about 30 seconds. Not quite enough time to go get a cup of coffee. Not quite enough time to unlock your phone and start scrolling whatever app it is. Maybe just enough time to lean back and look out your window. Think about how you could be more like Bob Ross. That guy's awesome. All right, training is wrapping up. Now, I happen to know that 1 epoch isn't really sufficient for faults, so I'm going to leave that training going on, and we're going to let a second epoch blow by. So it's bouncing. That means the wait files are being written to disk, so they're not forgotten. And then here we go on epoch number 2, and I'll get the caffeine going again here. All right, let's turn off training, and I'm going to turn the inference on, and there it is. It's in yellow. So now we've got a chance to turn off my labels and take a look at the inference that the machine has come up with, and it's okay. Now this is a training line, so you would expect it to be pretty decent, and it is. So at this point, we've trained for about 1 minute, and I've spent about 10 minutes labeling data. So we're not done. We're going to have to put in a little bit more effort. So I've decided I'm going to fine-tune. I'm going to add a few more faults that I think I missed the first time. Some of these really low throw faults might be important, and I'm going to get those scratched in there. Okay, let's step to a line we have not labeled yet and turn the inference on. And we can see it's okay. There's no false positives. Most of the faults have been picked up, but they haven't been completely scratched in, and I think we're still missing a handful of faults. So what I'm going to do is I'm going to take that inference and I'm going to turn it into labels. And that's kind of profound. What I've done is I've taken the machine's output and I've made it my own input. And so it's a way to speed up the effort. And here I am. I'm going to scratch in all the faults that I think the machine has missed. Well, now we're going to be up to 4 training images. I know we're going to go to 6 on this demo. And I'm going to look around for anything I think I might have missed. There's some other stuff on here which might be a fault, but it's a little tough and I don't want to overinterpret. So I'm going to hold off on those. And let's step to another line. Here's another line I've already labeled. Let's look at the inferences. Looks pretty good. Anything else I want to add? No, I think I'm cool. Let's step further east to a line that we haven't labeled yet. Now here's a line that's going to need some more work here. So I'm going to get up to the 5th of 6 lines that I'm going to label on this data set. And let's speed this up because there are a lot of faults on this line. Okay, now let's kick off another epoch of training. I think we're too deep, so I think this is the 3rd epoch of training here. Now I probably should have sped this up, but I didn't. I figured I had a captive audience. I could try out some of my new stand-up material. I'm an aspiring comic. So Srini, what is orange? And sounds just like a parrot. A carrot. He liked it. So if this whole seismic interpretation thing doesn't work out, I got a plan B. I got more of them, but training is too fast, so you're going to have to come back for another set. All right, so we're on 3 epochs. I want to poke around here. Those labels are looking much better. Let me step to another line to see how it's doing. Oh, I've let training go. I need to turn that off. And once I turn it off, I'll get my inference up. There we go. Okay, so this is some of the thickest, densest faulting there is in the data set. And I would suggest we're at a 80% solution after about 20 minutes worth of work here. It's pretty good, but I would suggest that we probably need to put more labels and do a bit more training to get it to a point where it's, say, 99% complete. So at this point, you really have to decide why are you interpreting in the first place? Are you doing exploration where you're okay with an 80% solution? If you are, then maybe you're done. But now I'm going to look at what the machine is suggesting. And even though this is a line that I trained on, it's starting to disagree with me. So I just moved the tip of that fault up and look at this. This is really cool. It found the fault down deep. And now I'm going to react to that and say, okay, I actually think that's one fault here. So that's really a great example of you and the machine sort of playing off one another like a tennis match. So I'm looking for yellow where I didn't quite get it right. And it looks like I kind of missed the tip out of that fault, so I'll add that one. Same thing over here on the left. Yeah, that middle one I'm not so sure about. I'm going to hold off on labeling that one. And then let's have a look around here. Oh, I've completely missed a couple of faults here that the machine has picked up on. So it's not just deferring to my training labels, it's actually free to disagree with me and point out the things that I missed. So we're starting to iterate. My labels are converging on it, and then every time I train, it's going to get closer toward my labels. Yeah, it's suggesting this fault comes all the way up and intersects. I'll buy that, so I'm going to bring that interpretation in too. And this one, I think I'm a little off. I'm being a little pedantic here, but I'm going to erase my interpretation and defer to the way the machine sees it. All right. So I'm going to do something cool here. I am going to go to my training menu and I'm going to reset the network. So it's going to forget everything it's learned because it was learning on some labels that were just okay. And now I've got a more mature set of labels, and I'm going to kick off 4 epochs of training in a row. And this is really cool. You're going to watch the first epoch come by, and you're going to see what training looks like after just one. And it's kind of weird. It's like dust everywhere. And then epoch 2 is going to fly by, and it's going to blow all that dust away. And then here comes a third epoch, and what will happen is all these fuzzy faults are going to sharpen up. And then the last epoch, the fourth, is going to blow away all these little false positive wispy things. Boom. And we've got a pretty well-trained network on a good set of labels. So if you ever hear anybody talking about explainability of neural networks, I think you just saw an example. I think every one of those epochs did something meaningful to a person when they watch it in real time go by. So now I'm going to step way out to the right side of the data set. There are no labels over here, and lo and behold, the fault patterns are different. I have not taught this machine anything about listric faults, so it hasn't gone out and interpreted them. So I feel obliged to add a few more labels. I think this is the last line that I'm going to label here, and I'm going to show the network that faults can go listric and parallel to bedding. So let me get these scratched in here, and let me connect up a few loose ends here. All right, and then I'm going to kick off a 5th and I think final round of training here, and we're going to see how the network reacts to these new labels. Oh wow, it's found some stuff that I totally missed. Yeah, there's some false positives out here. I'm not worried about those. But look, there's this natural spacing between these listric faults, and if we repeat that spacing to the right, it has found 2 new faults that I completely missed. And so now I'm going to start trusting the network more and say, okay, you know what? Those look like the right place in space. I can maybe see them. I'm going to defer to its expertise and scratch those in as real faults. So at this point, the machine is starting to see things that I don't really see at all with my eyes here. And then look here, I gave it a listric fault and it disagreed with me. And I might have over-interpreted that portion because we're up at the edge of the data. So I'm going to trust the network and put in a more conservative interpretation of these 2 faults here. All right, I think you see the workflow here. It's just a matter of how much accuracy you want to impose upon the training. If we were inclined, we could label some more of these dense lines here, take the inference, turn it into labels, and clean it up, and we could get to a 99% solution. But I think for our purposes today, I really just wanted to demonstrate the interactivity and how the machine and the expert work together to arrive at a solution. So what I'll do is I'm going to click training and I'm going to generate a probability cube. Now you can see I've only labeled 6 lines here. If I were doing this in a production setting, I probably would have labeled more like 20 or 30. But what I'll do is I'll take the network as it stands right now and we'll run every single line in the data set through the training that we've done. And we're going to output a static probability cube of faults. Now in real time this takes just a couple of minutes. So now it's time to get up and take a coffee break. And when we're done, we can still keep looking at the output, but now when let me let it catch up here. Now when we look at the data, we're not looking at a live inference that's hot off the GPU. Now this inference is the static one that exists on disk. So this is the final output of the application. Now we have a dense representation of all the faults in the data set. And if you like, you could convert this into fault segments if that's the way you want to consume your fault interpretation. Now, we don't have time to show the fault segmenter here for this webinar, but it is an adjunct functionality in AWS. So I'll end the demo right there, and I'll reiterate what Alex had mentioned earlier on. If you'd like to test drive the application running on AWS, you're welcome to visit this link. I think Alex will copy and paste it into the chat, and then we'll get you set up with some free credits from AWS and Bluware to try this out for yourself. So with that, I'm going to shut down the presentation and we'll pause for a minute or two to collect up some Q&A. First question I see is, how is this technique different from other market offering? I think what we're selling here is the interactivity. If you look at the network that we've deployed, it's actually a fairly generic UNet. So if you're a data scientist who's working to build some sort of next-gen object detection network, we're very open to that. We're happy to share the framework with you, and it's just a matter of bringing your TensorFlow network into our environment. And what we're trying to do is just to speed up the cycle time between what an expert sees with their labels and what the machine is inferring. Another question I see is, can you extract fault planes from the cube? Yes, we've implemented the Zhenming Wu approach, which is optimal surface voting. And so that's another output in addition to the probability cube, and that will output the faults as surfaces. Okay, Hyben is asking, how is the model network architecture defined or changed, updated? It's really up to you. If you become a client, then we're happy to assist you with getting your own networks built into the engine. We don't really think we have a proprietary network we're selling here. We're really just selling patterns of access to the data here. In fact, I'd be very open to seeing newer and better models getting put into interactive AI to maybe make your implementation of the software better than your competitor down the street. Matt is asking if Bluware is available on the marketplace. I presume you mean the AWS Marketplace? Sorry if you can jump in.
Yes, so I think in this case, the way this is going to work is this: the entire interactive AI works in your AWS tenant. So the application and the data, everything lives in your AWS tenant. Essentially, we don't host anything for you. It's private, and it's your copy, essentially. There is, Matt, there's another question at the very top. What are the limits on the view window? Can we see the data in 3D? Can we take slices along arbitrary angles? This is from Michael Morphew.
I see it. Limits of the view window. Right now, it's an entire line. So you're able to access the data via cardinal directions, inline, crossline, or z-slice. Can you see the data in 3D? I presume you mean perspective view. And interactive AI doesn't support 3D perspective right now. We have an adjacent application called Headwave where that functionality exists. Can we take slices around arbitrary angles? Presently today, no. I'm working on a technical solution to build into the product so you can come at it arbitrarily. But when I say arbitrarily, I mean arbitrary angles. I don't want to support fully random lines because that would be a nightmare to try to track, train on, and infer. So it's a work in progress. I see a question that says, can we see a demo of fluvial system segmentation labeling? Not for me, you can't. We do have clients who are doing that, but we don't really have any good data sets in order to demonstrate that technology. I would love to get my hands on a data set where that's pertinent, and because we have seen some success in using the same approach to extract channels. And so one thing we're thinking about is it's kind of tough to label fluvials in Z-slice mode, right? What you really want to do is start with a horizon stack and then label a couple of horizon slices and then let the thing go to town from top to bottom. And I can't show anything there because I don't have anything that's available with show rights, but I'm optimistic that this is it's a very obvious use case to try with interactive AI. Tanya's asking if we can set a data set from a combination of 3D and 2D seismic. How does it handle different vintages of 2D? Nope, just 3D right now. We've had conversations around supporting 2D, but we're still waiting to see enough of a market demand for 2D before we resource that functionality. Matt has another question. He's asking, can more compute be invoked in the backend for faster training? The answer is yes. The version that we're looking at today is version 2.1. It's just using a single node, if you will. What's under development right now is moving to a Kubernetes-based system where we can parallelize everything that can be parallelized, and that's going to allow us, it'll make everything go faster, and it'll also allow for you to label more than just one feature in a single session. That's still well underway, and we'll let you know when that functionality is ready for market. Okay, Engine is asking a pretty detailed question here. I'll read it out. You mentioned that user is expected to create labels that are supported by the seismic. Do you see benefit of using probabilities to infer predictions along places which are not imaged seismically? If it's designed to pick only places where it's clearly imaged, how would this differ from conventional auto-picking tools? So I showed you a data set that's pretty well imaged, and it's a pretty straightforward proposition to get faults out of the application. What we've seen in practice from users who are using this commercially is that it does work like in subsalt zones where the faults are just barely at the limit of being detected. But you have to adjust your expectations as to what the tool is going to do for you. It's not going to map out the entire fault network for you. Instead, what it's going to do is it's going to act like a flashlight. And it's just going to point out tiny hints of where it's picking up faults. And what we find is if you visualize that in a 3D environment, your mind will connect up some dots as to where these faults are that are only showing up on a handful of lines. And then you can come in there and sort of fill in the dots, sketch it in, and find faults that are just at the very limit of detection, maybe below your eye's ability to detect them and just above the ability of the machine to detect them. So it's a different workflow, but if you're desperately trying to find closure on some sort of subsalt fault prospect, then this tool might be able to help you find something if it's just barely there. What's the size of this volume? This is a small play volume. I think it's on this order of a gigabyte. At scale, if you're doing large, say, spec GOM surveys, then the current implementation, it might take hours to predict the probability cube. And I'll withhold an estimate as to how long that will take when we're running in a Kubernetes environment. It'll be faster. Matt has another question. Can the results be exported and brought into other software packages? Yeah, of course. The natural output of this product is a probability cube. And so typically what you'll do with that is you'll bring it back into Petrel or Decision Space and then use it as an overlay onto your seismic data. And I suspect in the coming years, instead of a probability cube just having one channel for faults, it's going to have a dozen channels for a dozen different feature classes. And that will be the overlay that you put on top of your base seismic. Yeah, that's the way I think the application ought to be evolving. Can we incorporate wells with seismic for deep learning in Bluware? One of the things that's underway right now is the ability to import wells and log curves. Today, we're just using that as a visual indicator as to where your well control is. We're not really planning on using the LAS digits to influence the deep learning network. Wits or Whites is asking if we're going to move on to horizon picking. I'd like to. I think it's a feature that everybody in the whole wide world uses, and every commercial implementation that I've used in the past I've always found something lacking. So actually a research project I was working on just maybe a year ago was using deep learning where you label one or two inlines and then let the machine label the rest of them. And we were having some initial success with that. And so I think that's fertile ground for R&D and to become a future product. Andrew Davids is asking if it's possible to incorporate constraints based on structural geology into the algorithm. Not to be cheeky, but you are the constraint, being the interpreter. So remember, the machine knows nothing about faults. It actually doesn't even know anything about seismic when you start training it. And if you want to train it poorly, you're going to get a poor prediction. So any sort of physical constraint that it manifests itself in your labels is going to show up in the inference here. So you're not explicitly putting physical constraints on the network, but they are implicit in the training and inference loop. Elia is asking if we do ML for shallow salt. Yeah, the two features that seem to be getting the most traction in the market right now are faults and salt. And I didn't demo it, but we have tools that were built specifically to detect and extract salt bodies from your data set. So it's there, it works. It's just that it's a learning process. So the strategies and the way you interact with the application is a little bit different for salts than it is for fault. So there's a bit of a learning curve here, and it gives you an ability to play the application like a musical instrument. Right? You can pick it up and be terrible with it, but it takes a little bit of time and effort to sort of get an intuitive understanding as to what the network is doing. But once you get to that point, you really are more than the sum of just the two parts. And that's a nice thought to end on. That was the last question, so I think we'll wrap it up. We're 2 minutes overdue anyway. Let me thank you all for paying attention to me for the past hour. I hope everyone is staying safe as the hurricane blows through. And feel free to reach out to me on via email or LinkedIn, and I'm happy to talk to you about what this application can do and where I think it's headed in the future.